Today's topic is an introduction to artificial intelligence. I'm going to start out by giving you some definitions and terminology that you'll need to understand the different concepts in artificial intelligence. Next, I'll lay out some of the theoretical basis for the thinking and work that we do in artificial intelligence. Lastly, I'll show you some examples of how we can use artificial intelligence concepts to solve some common problems that we encounter in robotics. Artificial intelligence is itself a huge field that you can study all on its own. I won't be going into detail here in any of the individual artificial intelligence methods. I'll just be giving a general overview of the broad concepts and how these different ideas work. My hope is to spark your interest in artificial intelligence so that you can look into it more on your own and learn more about this exciting field. So let's start out with some definitions and some terminology. Artificial intelligence is the study of how we can make a machine that can do things that we generally think of as being reserved for humans to do. Things like making decisions, solving problems, and learning from experience. This is not a comprehensive list of all that artificial intelligence encompasses. AI also includes things like knowledge representation. How can we get a robot to use stored knowledge to solve problems? But this is a brief list of some of the topics that we'll be looking at in this class and in robotics too. In artificial intelligence, we refer to the machine that is doing this decision-making, planning, learning kinds of activities. We call it an agent. An agent is something that perceives and acts in an environment. An agent is kind of like the mind of our robot. When we study artificial intelligence, we might do it by programming a robot and watching how the robot acts in the world, but we also might use a virtual agent. A virtual agent might not have a physical body. It would just act inside of a virtual environment. This allows us to study the behavior of the agent, that is, our algorithms that we've written to enact the artificial intelligence, separate of the behavior of the robot's physical body, its sensors, actuators, and things like that. An agent is defined by something called an agent function. The agent function specifies how the agent should behave in the world. Our agent function has to be something that we can actually program in a computer language. So the agent function can include mathematical functions, and it can also include algorithm elements like loops, conditional statements, and the like. Usually, we're not trying to make an AI that can operate in the actual physical world that we live in, because that's a very complex problem to solve. Usually, we invent a world in which the agent can operate to study how the agent will behave. We're usually doing this in order to simulate some specific scenario that actually does exist in the real world. And I'll give you an example of this using an AI simulation that's known as Vacuum World. In Vacuum World, we have a grid of locations where our agent can move to. Here, our agent is a vacuum, which is represented by this red square. Distributed throughout the vacuum world are these blue dots, which represent dirt. The job of our agent is to move around vacuum world and suck up the dirt. We usually want to optimize some function. For example, we might want the vacuum to move to the dirt and suck it up with as few moves as possible to optimize the amount of dirt collected for as few moves as possible. We also need to specify the rules of the world in which our agent will operate. For example, perhaps this vacuum can only perceive the squares that immediately touch it, so that the vacuum cannot see the locations of all of the spots of dirt distributed throughout the world. The definition of the world in which the agent operates defines the problem that we're trying to solve with our artificial intelligence. In this case, our problem is that we want the agent, in this case the vacuum, to move through vacuum world and collect all of the dirt with as few moves as possible, given the limitation that the vacuum, the agent, can only perceive whether or not there is dirt in squares that are touching it, not in all of the squares throughout the world. This restriction defines our problem, and we can now start to think about what kinds of artificial intelligence we could use to design the agent function to get the vacuum to move around the world and suck up the dirt. Now that we understand the definitions of some key terminology, including agent, agent function, the concept of a world, and the overall meaning of the term artificial intelligence, let's move on to the second part, theoretical basis for artificial intelligence. To help motivate our thinking about the theoretical basis for artificial intelligence, I'd like to start by showing you my all-time favorite clip from The Simpsons. In this clip, Homer and Bart want to participate in The Simpsons parody version of BattleBots. Since they don't have the skills to build an actual robot, Homer dresses up like a robot and participates in the challenge himself. In this clip, I want you to pay special attention to what the announcer says.
Come on, Homer. How long does it take to go to the bathroom? Huh? Dear Bart.
I'd love to be with you, but I just remembered an old army buddy has come to town. We'll meet you later. Love, Dad.
Well, I wish Homer was here. But don't worry, I've got a name all picked out for you. Chief Homer, let's win this one for Dad.
In this corner, operated by Frank Murray and Little Frankie Jr., Buzzkill. And in this corner, the challenger, Chief Homer.
There's no love lost between these emotionless devices.
Robots Rumble.
Oh, jeez, I'm the only one in the audience over 15.
Are you here with your children, sir?
Yeah, my two kids, Screw and you.
What's this? Homer has dropped his hammer.
Ho, ho! Doing it for the boy. Doing it for the boy. Pain is love. To bleed is to care.
Can robots feel pain? If so, we are horrible, horrible people.
He's killing him softly with his saw.
Killing him softly?
With his saw.
I mean, beep, beep.
In this clip, the announcer said the following: "Can robots feel pain? If so, we are horrible, horrible people." This is actually a good starting point for our thinking about the theoretical underpinnings of artificial intelligence. This statement illustrates a fundamental misunderstanding that people have about artificial intelligence that often results in thinking about artificial intelligence as if it's a mysterious or esoteric kind of a topic. When this one misunderstanding is cleared up, it becomes much easier to think about the concepts of artificial intelligence. Here's what the misunderstanding is. As a human being, we receive some inputs from the world through our senses. And we also produce an output on the world that we typically call our behavior. But between our perception and our behavior, we also have something else in the middle. We have a sort of internal experience of the world. For example, when we perceive some kind of a distressing event that occurs to us, we don't merely act as though we are in pain. We actually are in pain. We have an internal experience of pain. In the same way, when we perceive some pleasing or enjoyable event, we don't merely behave as though we are enjoying the event, but we have an internal experience of pleasure and enjoyment. In the same way, when we perceive experiences that cause us to learn, we don't simply behave as though we had learned. We have also an internal experience of learning new information and skills. The confusion about artificial intelligence that makes us think of it as such an unusual and mysterious kind of a topic comes when we think about artificial intelligence in terms of this internal experience. We wonder how we could possibly ever create a machine that would have an internal experience. But when we are trying to create an agent with some artificial intelligence, we don't focus on the internal experience at all. Instead, we have an agent that receives some perception through its sensors. And it produces an output of some kind of behavior. We make the assumption that between the perception and the behavior, there is nothing. The agent simply converts a perception to a behavior. As long as we think about artificial intelligence in this way, it becomes much easier to see how we could make a machine that would learn or make decisions. The agent in this case is not much different than any other system that we model or build. An agent is an algorithm that converts some perceptions into some kind of behavior. We're not trying to make an agent that actually learns. We're trying to make an agent that behaves as if it learns. Philosophically, it's unclear whether making an agent that behaves as if it learns is any different than making an agent that actually does learn, or if making an agent that acts as if it was experiencing pain or pleasure is any different than actually experiencing pain or pleasure. But for us robotics engineers who are programming agents, the distinction is more or less irrelevant. Our task is to create an agent that converts perceptions into behaviors in the way that we want it to, regardless of what actually is happening in its own internal experience. From here on out, we'll be focusing on how we can create an agent that converts perceptions into behaviors. When we consider how we want our agent to convert perception into behavior, there's one most fundamental question that we have to start out with, and that is, do we want the robot to behave like a human, or do we want the robot to behave rationally? Here, the word rational has a specific definition that may be different than the way that we typically think about rationality. In artificial intelligence, the word rational means that an agent maximizes its expected outcome given what it knows. Do you think that humans behave rationally under this definition of rational? Another way to state the definition of rational is to say that the agent always does what is the most good for itself. Philosophers and psychologists disagree about whether or not humans fundamentally behave rationally. In artificial intelligence, there are different camps of researchers that are studying the problem from different points of view. Some researchers are trying to come up with artificial intelligence that causes agents to behave as much like humans as possible. Other artificial intelligence researchers are trying to get the agent to always behave rationally. Let's look briefly at each of these problems. If we decide that we want the agent to think or behave like a human, the standard metric for how successful we are with that is something called the Turing test. The Turing test is named after a famous artificial intelligence researcher named Alan Turing. I have here a quote from one of Alan Turing's papers, which says, "I propose to consider the question, can machines think?" Turing proposed a test, now known as the Turing test, to decide whether or not an agent was sufficiently thinking or behaving like a human. Here's how the Turing test worked. A human subject would be brought into a room and would be placed at a table. And this table would have a barrier on top of the table so that the person cannot see what's on the other side of the table. On the other side of the table would be either another person or an agent, which in this case the agent is a computer. The human subject would be allowed to write questions on a piece of paper and send those questions across to the other side. The agent on the other side, whether it's a human agent or an artificially intelligent agent, would be able to write an answer on the piece of paper and send it back. The human subject would then make a decision as to whether the agent on the other side was a human or a machine. If the human subject cannot tell the difference between the human and the artificial agent, then the AI would be determined to be sufficiently thinking and or acting like a human. Another way to state the Turing test would be to say that a machine would be considered to be behaving like a human if the machine is able to deceive a human into thinking that it is human. Now, although Alan Turing lived from 1912 until 1954, the first time a machine successfully passed the Turing test was just this past summer in 2014. I encourage you to do some searching about this event and read about the machine that first passed the Turing test. Now that we've looked briefly at the issue of an agent behaving like a human, let's now switch and take a look at the issue of machines behaving rationally. In order to do that, we're going to move on to the third part of this lecture, which is some examples. Remember that an agent is defined by an agent function that specifies how it should behave in the world. We're going to take a look at a couple of examples of agent functions that result in a rational agent to operate in vacuum world. Remember that in vacuum world, we have a vacuum moving through this 10 by 10 grid to pick up pieces of dirt. The first type of agent function that we'll take a look at is called the simple reflex agent. This is the most simple version of an agent function that we could use to operate within vacuum world. A simple reflex agent selects actions on the basis of a set of condition-action rules. If we can come up with a series of rules that will allow the vacuum to find the dirt and suck it up, remember that the vacuum does not know the locations of all the dirt. The vacuum can only perceive whether or not there is dirt in the squares that are adjacent to it. We can write these condition-action rules in something called a decision tree. The simple reflex agent needs a decision tree to show it what to do in every kind of a situation. Each of the blocks in this decision tree that are blue represent things that the agent can determine with its sensors. In other words, it's things that the agent can perceive. The red blocks represent actions that the agent can take with its actuators. We have to be very careful when we're creating a decision tree not to include blocks that require the agent to know things that it cannot determine with its sensors, or that require the agent to do things that it cannot do with its actuators. In this decision tree, which is used for vacuum world, the agent starts by checking if it is currently on top of dirt. This is something that we are assuming that the agent can detect with its sensors. If it is on top of dirt, we will tell it to suck up the dirt. This is something that we are assuming that the agent is able to do with its actuators. If it is not currently on top of dirt, we will then check to see if it's in the first column. If it is in the first column and in an even row, it will go right. Otherwise, it will go up. If it's not in the first column, but it is in the last column and an even row, it will go up, otherwise go left. If it's neither in the first column nor the last column, it will then check if it's an even row, and if it is, go right, and if not, go left. This simple decision tree will cause the vacuum to visit every square in vacuum world and suck up the dirt whenever it's on top of a piece of dirt. The decision tree is not very optimized because it will require the vacuum to visit every square in the world. Simple reflex agents are typically not very optimized, but they are very simple. Decision trees and simple reflex agents will typically work as long as the problem is not too complicated a problem to solve. As soon as the problem becomes more complicated, the decision tree becomes more and more difficult to build and program into the agent. For example, if we would add barriers to vacuum world, we would have to add in rules that tell the vacuum what to do anytime it comes up against a barrier. Even this relatively simple complication can make the simple decision tree too complicated. Let's take a look at another type of agent function that can deal with more complex and unknown scenarios. To do that, let's first consider how people and animals decide what steps to take when pursuing a task. Remember we said that a rational agent is one that always does what is best for it in any situation. What is good for or bad for our vacuum in the vacuum world? In other words, can we punish or reward the vacuum? This may seem like a complicated and confusing philosophical question, but remember that we're not trying to think about the internal experience of the agent. We're just thinking about how the agent converts perceptions into behaviors. In other words, we're not trying to make the robot be punished or rewarded. We're just trying to make the robot act as though it were being punished or rewarded. We can do this using a kind of agent function that's called a utility-based agent. In this case, we're not going to give the robot or the agent any rules to follow. Instead, before each move, the agent is going to consider each possible move and ask, how happy will I be if I make that move? We're going to create a function called the utility function that describes how rewarded or how punished the agent is going to be. In order to do this, we have to decide what we should reward the agent for and what we should punish it for. In this case, we're trying to suck up the dirt as efficiently as possible. So we want the robot to be rewarded if it goes to a square with dirt in it. We want the robot to be punished if it goes to a square that it has already been to before. We also don't want the robot to go off the screen no matter what, so we'll punish it for that. And in fact, we'll punish it a lot for running off the screen, since we really don't want that to happen. So here's how we can construct our utility function. We're going to create one variable for everything that we want to either reward or punish the agent for. we'll have the variable v that represents the number of times a square has been visited. The variable d will be 1 if the square is dirty, and 0 if the square is not dirty. Variable s will be 1 if the square is off the screen, and 0 if it is on the screen. Each of these variables will be multiplied by a weight. The weight determines how much punished or rewarded the agent will be for that particular thing, so that weight 1 tells us how rewarded the agent should be if it goes to a square that is dirty. Weight 2 tells how much punished the agent should be if it goes back to a square that has been visited before. Weight 3 tells how much punished the agent should be if it drives off the screen. A weight will be negative if it represents a punishment, and positive if it represents a reward. The magnitude of the value tells how much punished or rewarded the agent will be. So in other words, a negative weight represents punishment. A positive weight represents reward. The greater the weight value, the more rewarding or punishing the thing is. We get to pick the weight values, but the variables d, v, and s will be different for each square that the agent is considering going to. Each time the robot is able to make a move, it will calculate the utility of each adjacent square. Whichever square has the highest utility will be the square it will go to. Remember that this is the definition of rational. In this case, the robot is always doing the thing that gives it the greatest reward, given what it knows. And in this case, all it knows is the state of each square around it. Now, we have to set values for each of the weights. Here's a set of weights that I chose for this case. I set weight 1 to be 10, weight 2 to be -1, and weight 3 to be -1 billion. Now, why did I choose these values? The magnitude of each of these values represents how rewarding or punishing I want each thing to be. Weight 3 is multiplied by s in our function. Remember that s represents whether the square is on the screen or off the screen. Since I really don't want the robot to ever drive off the screen, I make weight 3 to have a much greater magnitude than any of the other weights. Since weight 3 much greater magnitude, the agent will never drive off the screen, regardless of whether each square has been visited before or whether any square has dirt. Now, I also made weight 1 to be 10 times greater in magnitude than weight 2. Weight 1 is multiplied by d, which represents whether or not a square has dirt in it. Weight 2 is multiplied by v, the variable that represents how many times a square has been visited. I did this because I want the robot to go to a square that has dirt in it, even if that square has been visited before. It's possible that the square has gotten dirty since the robot last visited that square. Utility agents are much better than simple reflex agents for tasks that are complex, especially when there are unknown variations in the task or the environment. Let's consider what we would have to change here if we introduce barriers into the environment. If we have a new element in the environment, like barriers, all we have to change is the utility function. Here, I've introduced a new variable, b, which represents whether or not there is a barrier in a given direction. b is multiplied by a new weight, w4. I've set the value of w4 to be negative to represent that the agent will be punished if it drives into a barrier. Notice that I set the magnitude of weight 4 for the barrier to be much less than weight 3, which represents how punished the robot would be if it drove off the screen. I would rather the robot try to drive into a barrier rather than try to drive off a cliff. But the magnitude of the weight on the barriers is still greater than the weight representing the dirt or whether a square has been visited before. I'd rather a robot not try to drive through a barrier in order to get some dirt. And I'd also rather that the robot not try to drive into a barrier because another square that does not have a barrier has been visited before. This change that I had to make to the utility function to deal with the barriers is much simpler than the kind of changes I would have to make to the decision tree in order to deal with the barriers. In general, utility agents are much better than simple reflex agents for tasks that are complex. So far, we've looked at some definitions, including agent, agent function, the idea of a world, and the overall idea of artificial intelligence. We then looked at some theoretical basis, including the difference between behavior and internal experience. And we also looked at the difference between human behavior and rational behavior in terms of how we want our AI or our agent to behave. We looked briefly at the Turing test as a way to determine whether an agent successfully exhibits human behavior. Then we looked at a couple of examples, including the simple reflex agent and the utility agent. The last example that I'm going to show here is a third kind of agent called a learning agent. Remember what we said earlier about how humans convert a perception into behavior, but they also have an internal experience. If we can create a model, ignoring the internal experience, of how the human converts a perception into behavior, we can then use that model for our agent to define how it should convert perception to behavior. In the case of a learning agent, what we want to do is we want to create a model of how human beings convert perception into behavior when they learn a new concept. Note that this does not necessarily have to be a human. We could use an animal in this example also, if we want the agent to imitate the behavior of the animal. To help motivate our thinking about how humans or animals convert perceptions into behaviors when learning, I'm going to show you one of my favorite clips from The Big Bang Theory.
Are you finished?
Well, thank you. How thoughtful. Would you like a chocolate?
Yeah, sure. Thanks. Oh, sorry, Sheldon. I almost sat in your spot.
Did you? I didn't notice. Have a chocolate.
Thank you.
You're here a lot now.
Oh, am I talking too much? I'm sorry. Zip.
Thank you. Chocolate?
Yes, please. Oh, hey, Kim. Yeah, you know what? Hold on. Let me take this in the hall. You'll never guess who they got to replace you with.
Okay. I know what you're doing.
Really?
Yes. You're using chocolates as positive reinforcement for what you consider correct behavior.
Very good. Chocolate?
No, I don't want
This clip showed an example of reinforcement learning. In reinforcement learning, the model that converts perception to behavior is a statistical model. The statistical model works like this. An agent's behavior consists of actions that the agent decides to take. A perception tells the agent how good or bad were the results of the chosen behavior. Initially, the agent will randomly choose which behavior to take. Let's write this in the form of a flowchart. When the agent's learning algorithm begins, the probabilities for each possible action that the agent could take are set to equal values. In other words, every action that the agent could possibly take is equally likely to be chosen by the agent. Next, the agent makes a choice of which action to take based on the probabilities. At this point, when the probabilities are all equal values, the agent is deciding an action randomly. Next, the agent perceives the effect of the action. Specifically, the agent needs to perceive whether the effects of the action were good effects or bad effects. The effects of the action are then used to update the probabilities. In other words, if the effect of the action was a positive effect, then the probability of repeating that same action will increase. If the effects of the action were negative, then the probability that the agent will take that action again will be decreased. We now loop back to again decide an action based on probabilities. And we again perceive the effects of the action and update the probabilities. As this loop continues to execute, it will become more and more likely that the agent will repeat actions that resulted in positive effects, and less likely that the agent will repeat actions that resulted in negative effects. Over time, the agent will learn which actions are best, or, in other words, the agent will act as though it had learned which actions are the best, because those actions will be repeated. Let me show you briefly how this could work in Vacuum World. In Vacuum World, many times the agent has a number of choices that give equal utility. For example, in the very first move that the agent makes, moving to the right and moving up have the same utility. Neither of the squares have been visited before, and neither of the squares have dirt. Also, neither of those two squares is running off of the edge of the screen. So the two actions, go up and go right, have equal probabilities. If our agent is not a learning agent, it will have an equal likelihood of going up or going to the right. But we could change its algorithm to make it a learning algorithm. In a learning algorithm, every time the vacuum successfully sucks up dirt, we will change the probabilities of each action in the future decisions so that it will be more likely to move back to the location where it has sucked up dirt in the past. Now, note that learning agents do not perform very well when there's nothing to learn. In Vacuum World, we might distribute the dirt randomly throughout the screen. In this case, there isn't any possibility of the vacuum learning what areas are more likely to contain dirt, because there are no areas in the screen that are more likely to contain dirt than other areas. But suppose that we change the way that we distribute the dirt on the screen. For example, suppose that the upper left-hand area of this screen represents a place where people or animals go more frequently, and so those areas are more likely to contain dirt than other areas of the screen. In this case, the learning agent would be able to learn which areas of the screen are more likely to contain dirt, because every time it successfully sucks up dirt, it becomes more likely to choose to move back into that area of the screen. There are many other approaches to learning besides reinforcement learning. We can use learning approaches that involve a teacher, known as supervised learning approaches. Or we could use learning approaches that have neither a teacher giving the right answer nor any feedback regarding which actions were better than others. That's known as unsupervised learning. In any case, learning approaches are only useful when there is something to learn. Usually, the things that there are to learn have to do with patterns. Patterns like where dirt is located in vacuum world, or patterns that occur in other data that the agent can gather from its environment. So, in conclusion, artificial intelligence is all about making robots behave as if they are thinking, learning, making decisions, and other such functions that are typically regarded as being human kinds of functions. By making robots behave as if they are performing these human-like functions, we can greatly simplify the coding for performing tasks that are complex, unknown, or even dynamically changing environments.